Sergey Stanchits, and Sergey is, as you can see, he is the head of acoustic technology and a senior research scientist at Schlumberger's Innovation Center in town here. And he received an MS in electronic engineering and a PhD in mathematics. And his PhD thesis was entitled Radiation of Elastic Waves by Growing Cracks. And for 35 years, Sergey has been working on this particular topic, including 5 years at the U.S. Geologic Survey in Menlo Park, and quite some time, more than 10 years at the German Geoscience Center in Potsdam, and looking at compaction bands, borehole breakouts, and things like that. And particularly in the last 3 years or so, is it 3 years?
Yeah.
With Schlumberger, he's been really looking at hydraulic fractures growing towards interfaces and things like this. And so I'm really looking forward to this talk, and I welcome Sergey.
Thank you. Thank you. And first of all, I would like to say thanks to John for this invitation to the University of Utah. This is my actually first presentation at the University of Utah, and I'm really glad to be here and to describe our results obtained in laboratory. One of the main techniques, as John mentioned, in laboratory we use acoustic emission. And acoustic emission could be considered analogical to the registration of microseismicity in the Earth, just in the higher frequency range. And it is well known that in the field it's very important to investigate propagation of hydraulic fracture. And microseismic observation is one of the useful tools to demonstrate extent of hydraulic fracture and also the propagation of hydraulic fracture through some boundaries of complexity. And therefore we performed the series of our laboratory research in TerraTek, investigating hydraulic fracture propagation, initiation and propagation in intact homogeneous blocks, in the blocks with artificially created interfaces, and also in naturally heterogeneous and blocks of shale with a high degree of geometrical complexity. And I will show you overview of our results. And first of all, I'm going to demonstrate you, as introduction, I'm going to demonstrate you some applications of acoustic emission for monitoring of rock fracturing at different conditions. As John mentioned, I worked in Germany, also applying acoustic emission for registration of fracture, and I will show you some examples. And then I will show you experimental setup of TerraTek and the results of hydraulic fracture monitoring using acoustic emission technique, ultrasonic transmission technique measuring ultrasonic velocities in the rock, and also volumetric deformation measurements. And finally, it comes a conclusion, and I will try to finish approximately in 45 minutes. And first of all, as introduction, John already mentioned about this. You probably can guess from my accent that originally I'm from Russia, and more than 20 years I worked in Academy of Science of Russia in the Laboratory of Physics of Fracture. I have got my PhD diploma in Russia, but then after collapse of the Soviet Union, I moved to U.S. Geological Survey, where I worked about 5 years, and then I have been invited to work in Germany, in German Research Center, and I had a permanent position in Germany, and everything was set up for pure scientific research until 3 years ago. Roberto Suarez Rivera and Sidney Green convinced me to change my pure academic research to the challenging research in TerraTek, Schlumberger company. And therefore I relocated to Utah about 3 years ago. Through whole my career, I always used acoustic emission. As John mentioned, more than 35 years, I always use acoustic emission to registration of cracking on different scales, starting from micro scale, from cracking of grains, and up to studying of preparation of earthquakes in the deepest underground mines in South Africa, in deepest gold mines. And in all this research, I always use acoustic emission technique to register cracking, because it's a really powerful tool to investigate is going on inside the stress body. And today I will show you some overview of acoustic emission application. And at first I'm going to start with the application of acoustic emission for research fracturing of rock that I performed in Germany. And I would like to mention this setup because now together with my colleagues, Eric Edelman, we started a very similar research in TerraTek. And in this case, in Germany, I investigated samples, cylindrical samples of 50 millimeters diameter. The sample was installed inside a rubber jacket, as you can see on the photo on the right part of the slide. And we glued 16 P-wave transducers and also 8 shear wave polarized sensors directly to the rock, as you can see on the photo. And also we installed strain gauges and deformation measurements tool to the rock. And during fracturing of the rock, acoustic emission sensors register elastic waves, and using these elastic waves we triangulate and localize cracking. But it's clear that for accurate localization, it's necessary to know velocity in the rock as precise as possible, and therefore we use the sum of sensors for periodic sending pulses through the rock, and to measure time-dependent and stress-dependent elastic velocity in the rock during process of fracture. And as a result of this precise velocity measurement, it was possible to achieve in my research in Germany accuracy of acoustic emission high pass centers localization about plus minus 2 millimeters. And next slide shows our technique of separation of acoustic emission events. About 15 years ago, we proposed to use the first motion polarity of elastic waves to separate tensile, shear, and for collapse cracking. We used just the signs of first motion, and if majority of sensors register the motion direction outside of the sample, then we assume that this is the tensile type or T-type, because the motion of sensors pointing outside. If the first motion sign was inside the rock, then we assume that this is the pore collapse, the signal. And if the motions demonstrated almost equal number of positive and negative first motions, then we assume that this type of signals belongs to S-type or shear cracks. And this technique is really very simple. Right now in TerraTek, we initiated work of using full moment tensor analysis for more detailed analysis of source function. But I will show you that even this simplified technique can give us some information about type of cracking that we register during the process of fracture. And the next slide shows on the left side, you can see the photo of a sandstone sample after the test impregnated with the blue color of epoxy. And this blue color demonstrates the created fault. The sample was loaded under confining pressure, 40 MPa confining pressure, until failure. And in the middle part of the slide, I demonstrate animation of acoustic emission signals. This is just each dot corresponds to the acoustic emission signal. And I especially put a different color for different types of events. I would like to point out your attention that tensile cracks I marked as the pink triangles, and the shear type of cracks as the green circles. And you can see that at the very beginning of loading, of the very beginning of fracture, this is the stage of beginning of fracture, you can see majority of pink triangles spread almost equally, almost uniformly in the rock. But then later, it appears fault nucleation, and then shear fault propagates through the rock, and you can see pretty close correspondence of the shape of the fault and actually fault after the fracturing of the rock. And on the right part of the slide, I demonstrated different parameters plotted versus axial strength of the sample. And I would like to mention that especially for this kind of test, I implemented acoustic emission feedback control of loading, and this feedback control allow us to reach the failure point very gently, and even to investigate post-failure, post-peak region, because the loading regime was really related to the activity of acoustic emission. And in this case, before a failure, when acoustic emission activity was very high, we removed load and we even unloaded sample. And therefore, you can see a loading curve. After passing the maximal deformation, sample was unloaded and slightly, and you can see that in this post-peak regime, we had a formation of shear fault. And also, I would like to point out that at the very beginning of loading, we had approximately 80% of all signals identified as tensile cracks. Pink color on this plot corresponds T-type or tensile cracks. But then later, during loading, we had significant decrease of this tensile cracking, and we had a big portion of green sector indicating shear cracks, and as you can see from animation, that as soon as fault starts formation, we can see shear cracking related to the fault. And also what I would like to point out based on this result, that in the middle part of the slide, I demonstrated velocity, dependence of velocity versus axial strain. And you can see that at the beginning of loading, we had a homogeneous rock with equal velocity in all directions. But then later, we had a slight increase of axial velocity, and at the same time, we had significant decrease of horizontal velocities. And I would like to point out that I especially plotted velocities measured at different parts of the samples. And you can see that there is significant heterogeneity of velocity. That velocity, for example, in the middle part of the sample is significantly lower than velocity in the top part of the sample measured in horizontal direction. In order to localize precisely acoustic emission events, we applied this velocity directly measured during the test for algorithm of localization. And taking into account this anisotropic and heterogeneous velocity model, we reach a pretty good accuracy of our localization. And the next example that I would like to demonstrate is the water injection in the stressed rock. At first, I brought a sample pretty close to failure using this acoustic emission feedback technique, and then water was injected on the bottom part of the sample. And you can see that on the left part of the slide, I demonstrated different parameters plotted versus time after injection. And I would like to point out your attention that this red dot represents position of acoustic emission hypercenters. And the blue line is directly measured position of waterfront that we calculated directly from measurements of injected volume. And therefore, this blue line and the red dots are completely independent measurements, but you can see close correspondence between this position of waterfront and acoustic emission events induced by water injection. And actually, you can see the same on this animation presented on the right part of the slide, that the height of this blue bar corresponds to the position of waterfront at each moment, and the dots represent two orthogonal projections of acoustic emission hypercenters. And during injection, we performed acoustic emission ultrasonic velocity measurements. The position of traces where we measured velocity is marked by arrows and different color in this part of the plot, and also it's marked on the plot with the progression of acoustic emission cloud, and the result of velocity measurements presented in the left part of the slide. You can see a significant delay between velocity measured at different positions. And you can see that velocity shifted with the progression of fluid front. And therefore, during this experiment, we can obtain good comparison of results of three completely independent measurements. First of all, position of waterfront calculated directly from the volume of injected fluid corresponds pretty close to the front of induced acoustic emission events, and also it corresponds close to the beginning of the change of expected velocity. We interpret increase of velocities as a saturation of certain trace, and you can see that saturation of each trace is delayed in respect with waterfront propagation. And therefore, this kind of research demonstrated us that velocity measurements is a very sensitive tool to measure position of fluid front, And acoustic emission also can indicate the position of acoustic emission events induced by fluid injection. But as I mentioned at the beginning of the description of this experiment, at first it was necessary to bring sample very close to failure, because when we performed a similar test with the smaller axial load, when the sample was not close to failure, it was no high indication of induced acoustic emission events, because in this case it was necessary to bring the sample close to failure, but still to have it not at the point of the failure. And then injection of water with the small pressure, the pore pressure was only 5 MPa, but it just shifts Amor column envelope, shifted circle, and therefore we can reach the condition of failure at the place where we have water from propagation inside rock. And therefore this kind of research demonstrated us that acoustic emission could be a very powerful tool to investigate induced fracturing of the rock. And next example that I would like to show is the registration of compaction bonds. This was a sandstone sample with a porosity about 20%, and the photo of fractured sample presented on the left side of the slide, and the dark blue color indicates epoxy. We impregnated the sample after the test, but light color lines that you can see directly on the photo show us compaction bonds. Compaction bonds is the parts of the rock with the significant amount of crushed grains. And we investigated microstructure of crushed rock and demonstrated that the porosity of rock inside compaction band is around 5%, while the porosity of the rock surrounding compaction bands about 20%. Therefore, there is significant reduction of porosity in compaction bands, and it is well known that very often in the field compaction bands produce barriers for fluid propagation in the earth. And you can see on the middle slide I demonstrated acoustic emission results, and you can see pretty good correlation between the results of acoustic emission measurements and the results of direct position of compaction bands seen on the photo. And I especially marked by arrows some kinks of compaction bands, and you can find a similar kink on the photo. And therefore, this kind of research demonstrated us that really acoustic emission has accuracy around 2 millimeters, because the scale is presented on the bottom of the photo, and the diameter of the sample was 50 millimeters, as I mentioned at the beginning. And acoustic emission allows us to investigate dynamic of fracturing, what's happened, how it's happened, and what was the first and what was the later. And the next slide just shows two orthogonal projections of acoustic emission migration during increase of axial strain. And you can see that acoustic emission allows us to see that compaction bands were nucleated somewhere and then propagated, and also we can observe branching of compaction bands and tuning, and therefore we can see whole dynamic in a 3D space, how this complicated process of fracture is going on versus time, because photo of the sample can show us only a final picture after the test, but acoustic emission allows us to look inside sample and tell how this process of fracture going on during the fracture. And the very last example that I'm going to demonstrate you from my German research is the formation of borehole breakouts under pure hydrostatic pressure. It is well known that borehole breakouts is widely used in the earth to determine direction of the stresses. Well-known maps of the stresses in the earth made by Mark Zobak based on the direction determined by borehole breakout. And also there are numerous laboratory research demonstrating that in the laboratory breakouts always propagate in the direction of minimal principal stress. For example, like Bitzal Heimson demonstrated decades ago, and it's confirmed in many other tests. And we decided to investigate formation of borehole breakout under pure hydrostatic pressure. In this case, sigma 1 was equal to sigma 2 and sigma 3. There was no stress difference in the applied to the rock, but we have found that very soon after initiation of borehole breakout, we observed stress concentration at the point of initiation, and then this breakout propagated through the rock, driven by local stress concentrators created at the tip of the damage zone. We installed strain gauges around the rock, and we demonstrated that right after initiation, we have a change of strain of the sample. Before, strain of the sample was uniform because we had homogeneous rock without any stress concentrators. But then, after initiation of breakout, it was stress concentration near the tip of damage zone, and this stress concentration push breakout propagating through the whole rock. And acoustic emission, you can see, is a very powerful tool to indicate, first of all, initiation of this borehole breakout, and then also propagation. Results of borehole breakout is similar with hydraulic fracture that I will demonstrate you later, but I would like to point out that it's completely different mechanism. That's borehole breakout related to the crushing of grains and compaction of the rock, while hydraulic fracture is opposite. It's exactly opposite, because in hydraulic fracture we have a tensile fracture and by fluid injection. And in this case, it was just constant pore pressure and increasing compounding pressure. And that's just like an overview of my German part of research. And as a summary, I can tell you that acoustic emission allow us to look in details of fracturing of the rock at completely different conditions. And now let's look at our facilities, overview of facilities of TerraTek. Probably some of you know that more than 30 years ago, TerraTek built two loading frames for different size of the samples. And there is a possibility to apply through triaxial stress up to a few thousand psi at a different direction, and it's also a possibility to inject fluid and investigate hydraulic fracture. And in our research, we investigated three kinds of the rocks. At first, I will show you results obtained with homogeneous rock, without any planes of weaknesses. It was a sandstone sample. Then we performed a series of research together with Jeff Land, when we cut a sample of sandstone sample in two pieces, and then we glued together two pieces together in the periphery and investigated propagation of hydraulic fracture through these artificially created discontinuities. And recently, we performed series of experiments on natural shale. And photo on the right part of the slide demonstrates you the photo of shale sample before fracture. And especially to make this photo, we wiped the surface of the rock with the mineral spirit that evaporates very quickly from the flat surfaces, and it remains stuck inside thin cracks. And you can see complicated structure of the shale before beginning of the test. And we performed modeling of artificial discontinuity in order to model natural planes of weaknesses and discontinuities in the shale. And we investigated hydraulic fracture propagation with different fluid viscosities and different injection rates, and to investigate conditions of successful hydraulic fracturing. And at first, I will show you briefly our experimental setup. Our acoustic emission sensors were either embedded in the rock or embedded in the loading plates. Now we have technique with the sensors embedded in the plates. It became much easier to install rock and investigate hydraulic fracture. And then we inject fluid inside the borehole, and acoustic emission sensors allow us to localize coordinates using our data acquisition system. And next slide shows results obtained on our homogeneous sandstone blocks. That's just for reference. I show you that the plots on the upper part of the slide demonstrate three orthogonal projections of acoustic emission coordinates. And I use the color code of each dot according to the color bar presented on the bottom part of the slide. I especially decided to use this color code in order to demonstrate earliest events with the pink color, and then it goes according to rainbow color code, green, blue, and red. And red is the most recent acoustic emission event. And therefore, from color code of acoustic emission events, you can see a time sequence and progression of acoustic emission. And on the lower part of the slide, I demonstrate you different parameters registered during our hydraulic fracture, we injected fluid with a constant rate. This pink curve represents just the straight line of injected volume. And then on some moment we observed during this injection we measured bore pressure just directly by a sensor installed on the rock. And also, in addition, we measured volume. It's marked by its east-west volume. East-west direction is the parallel to the direction of maximal horizontal stress. And in this case, by flat jacks installed parallel to the hydraulic fracture, we can measure volumetric deformation of the rock. And deviation of volume from a constant value demonstrates us that we observed volumetric deformation of the rock. Unfortunately, green pointer is not working, and I will take mine. Yes, and you can see that at some moment we have beginning of this deviation of volume, and this volume shows us that decreasing of volume indicates that fluids inside flat jacks were pushed out of the flat jacks. It means that sample became bigger in size. We registered dilatancy of the sample, and this moment of beginning of sample dilatancy corresponds very close to the beginning of acoustic emission. You can see that earlier, before breakdown, we observed the propagation of hydraulic fracture, and completely independent measurements was the volumetric deformation measurement. And next slide on the left side shows the photo of the sample after the test, just split in two pieces, and dark red color shows a nice pancake shape of hydraulic fracture. In case of homogeneous rock, we observe it quite often, this nice pancake shape. And acoustic emission animation presented on the right side of the slide shows acoustic emission localization near the open section, marked by dark gray cylinder, and propagation toward the surface of the rock. I especially stopped accumulation of acoustic emission in the moment of breakdown. And therefore you can see that at the moment of breakdown, acoustic emission cloud propagated approximately half distance between borehole and the surface of the rock. And therefore we have obtained a completely independent confirmation that hydraulic fracture was initiated significantly earlier than breakdown in case of high viscosity fluid. We investigated similar hydraulic fracturing at different viscosities. And in addition to just plotting dots, we calculated density of acoustic emission events. In this case, I used a sliding cube inside our sample, our block with 5 millimeter size, and I calculated density of acoustic emission events inside this cube. And just this density plot shows very nice comparison with the shape of actual hydraulic fracture, that it's very close to pancake shape. And you can see also that hydraulic fracture continue propagation toward the boundary even after withdrawing of fluids from the borehole. Because in this case we were withdrawing not very fast, and hydraulic fracture was close to the boundary, and you can see that injected volume goes down, but hydraulic fracture still propagates over the surface. And therefore we learned how we can arrest the fracture in this kind of test, especially in order to investigate in details this arrested fracture behavior. And the next slide shows just comparison of different parameters plotted versus bore pressure. On the low plot by red dots, you can see a y-axis of localized acoustic emission events plotted versus bore pressure. And you can see that we applied some criteria. It's very important for practical application of microseismic observations or acoustic emission to identify the moment of hydraulic fracture initiation. And we applied statistical criteria described in our ARMA paper, that using this statistical analysis of correlation coefficient, we can pick up the moment of hydraulic fracture initiation. And especially in test that we call test number 3, we interrupted injection on pretty early stage before approaching the maximum borehole breakdown. In test number 1, I demonstrated you localization in previous slides. We had a propagation towards the boundary, and you can see that red dots touch the boundary. And in test number 2, we stopped propagation on significantly earlier stage because we especially tested this criteria of hydraulic fracture initiation works pretty good, and in real-time model we can monitor initiation of hydraulic fracture using acoustic emission, blue curve on the upper plot, and volumetric deformation measurements in real-time model. And it allows us to interrupt injection in test number 3 and withdraw fluid really very fast in order to arrest fracture and in order to investigate the structure of hydraulic fracture. And photo on the left side of the slide shows the cross-section of sandstone sample. It was a Colton sandstone sample, and you can see this dark color near the borehole. This is the borehole. And this dark color indicates area where we have fluid penetration inside the rock. And we, by yellow rectangles, I marked the area where we investigated thin sections. And the thin sections called A, obtained from the small distance from the borehole, demonstrate significant leak-off region. We estimated the width of this leak-off region about 1 or 1.5 millimeter, but on the higher distance, on the distance more than 20 millimeters of from the borehole, where we obtained the thin section called B, we can see no presence of oil at all, but we still can see dry fractures, and in many cases, these dry fractures just show us like the patches of fracture. Most of them propagate between grains, but with the APM analysis, we really proved that this is a real fracture, and you can see close correlation with acoustic emission results. That acoustic emission we obtained both in the area where we have fluid and we have dry fracture, and color code of acoustic emission, again, as earlier, correspond to this rainbow color code. And you can see that acoustic emission of red color appears on the latest stage of fracture, and they were created by pure dry hydraulic fracture. Especially in this test, we used the high viscosity fluid with 2.5 million centipoise, and in this case, fluid was unable to propagate on the very high distance. And we found a pretty good correlation between SEM images and acoustic emission. And in addition, as I mentioned before, that in addition to acoustic emission, we performed ultrasonic transmission. In this test, we had one sensor installed on the side parallel to the hydraulic fracture. Once per second, we sent pulse from this sensor and measured velocity in different directions. And the variation of relative normalized velocities and normalized amplitude of transmission shown on this slide. And you can see sequence of velocity variation. Actually, it's very similar with results that I demonstrated to you earlier that I obtained in Germany. There is a certain delay of beginning of velocity variation along certain trace. The value of velocity change is not very big because you can see that only 5% of highest velocity change, but still we can measure velocities pretty reliably. And also velocity gives us confirmation that before breakdown, we observed some velocity change, and this increase of velocity we relate to the saturation of rock surrounding hydraulic fracture and the drop of amplitude also associated to the partial saturation of the rock during this process of hydraulic fracture. And just to show you comparison of velocity measurements with acoustic emission, I made this animation where I especially highlighted each of ultrasonic transmission trace at the moment when we observed a drop of amplitude down to 80% level. I selected only just for comparison purpose, but you can see that there is a pretty good correlation between position of this ultrasonic transmission trace and propagation of acoustic emission cloud. These results, acoustic emission and velocity measurements were obtained completely independent because we used just the same sensors, but they were completely independent measurements. And you can see how that amplitude and the velocity change on certain traces with some delay during this hydraulic fracture propagation. And we think that it gives us completely independent confirmation that definitely we have a process of fracture initiated significantly earlier than the peak of bore pressure was reached. And we performed different kind of research in our triaxial cells, and I decided to demonstrate one of them with horizontal fracture propagation. This kind of research was performed when we applied the smallest stress in the vertical direction, and it was the modeling of horizontal completion. And you can see a nice shape of hydraulic fracture, very close to the photo of a fractured sample presented on the right part of the slide. And you can see how hydraulic fracture propagates, and acoustic emission can help us to not just to identify the initiation of hydraulic fracture, but also we can estimate the speed of this cloud propagation and the size and extent and whole dynamic of hydraulic fracture propagation in both horizontal and vertical completion. And as I mentioned before, we performed also tests with the artificially created plane of weakness. Actually, it was a block cut into pieces and then glued together in the periphery. And from animation presented in the middle part of the slide, you can see that hydraulic fracture at first propagated towards discontinuity, and then it was a spreading of hydraulic fracture up and down along discontinuity, and also east and west along discontinuity, because you can see this process was really a process of propagation of hydraulic fracture was delayed in the discontinuity, and later hydraulic fracture propagated through the whole block. And in that experiment we registered a little bit unusual response of bore pressure and also east volume, that we observed two steps in the east volume measurements. And acoustic emission is the only technique that allowed us to identify what was the reason of this first drop and what was the reason of second drop. You can see that at the beginning, at the moment of first drop, close to the breakdown, we have a hydraulic fracture reaching the interfaces. And then it was a pretty long process, about 10 minutes of propagation of fluid along interface and up and down. And only later, with some delay, we observed second drop of east-west volume measured by flat jack, and propagation of hydraulic fracture through the rock and from the borehole to the north surface of the block. And next slide shows us a comparison with the results of ultrasonic measurements. You can see, as I mentioned, acoustic emission clearly demonstrates that this was a process was delayed in the interface, and only later we observed propagation of hydraulic fracture through this interface. And just by color code on this animation, you can see that it was a spreading of hydraulic fracture up and down, and also left and right. Just on this particular moment, you can see dynamic of hydraulic fracture propagation. And independently performed results of ultrasonic velocity measurements show us some delay of velocity and amplitude measurements before breakdown, but I would like to point out your attention on this blue trace. Blue trace was outside of the borehole on the opposite side of the artificial interface. And you can see significant delay of increase of velocity measured along this blue trace. And it gives us a completely independent confirmation that fracture propagation from the borehole towards this north face of the block was significantly delayed. And therefore, we have completely independent confirmation by volumetric measurements, acoustic emission, demonstrating localization of hydraulic fracture, and also velocity measurements. All three independent measurements demonstrated to us the dynamic of this process of hydraulic fracture propagation through interface. And in this series of research, we have found that in case of high viscosity fluid, hydraulic fracture most likely propagates through the interfaces without any problem. But in case of small viscosity fluid or small ejection rate, very often we have this process of spreading of acoustic emission cloud, indicating propagation of fluid along interfaces. And that's conclusion that we made based on our sandstone homogeneous block research help us for interpretation of results obtained on the shale. And let's now look on the shale results. This was the shale block of 11 by 11 by 15 inches, the same size, and with the same geometry and almost the same stress as before, and with very high viscosity fluid. You can see that also in this case we observed symmetrical propagation of hydraulic fracture from both sides of the borehole, but in comparison with the sandstone sample, you can see that our acoustic emission cloud was significantly shifted below this open hole section region. And we have an assumption that it's related to the containment because of the bedding planes. And therefore the fracture was propagating in the low part of the block, and it was almost no fracture in the upper part of the block. But in the shale with the high viscosity fluid, we observed also initiation of hydraulic fracture significantly earlier than breakdown, something like 20 minutes earlier, and with significantly low pressure. And propagation of hydraulic fracture was really similar with the propagation in homogeneous sandstone blocks. In case of using water, we have found completely different results. First of all, in case of water injection with 1 centipoise viscosity, we observed beginning of hydraulic fracture initiation after the moment of breakdown. This red curve shows bore pressure. In all other tests with the high viscosity fluid, we always observe hydraulic fracture initiation earlier than breakdown. But with water, it was almost simultaneously, and our explanation that water has a tendency to penetrate inside open fracture as fast as hydraulic fracture propagates, because water always follows hydraulic fracture pattern. And also what was puzzling us that in this test we observed only one week of hydraulic fracture propagation. You can see that it was absolutely no hydraulic fracture on the second part. And actually when we cut block in few sections, if you visit TerraTek, you can see these slices of the block laying on our display, and clear there is no fracture on the opposite side of the block. Hydraulic fracture propagated only in one direction, and our explanation that it was some weak spot in this part of the borehole that hydraulic fracture was initiated on this part of the borehole. And right after initiation, we observed a drop of bore pressure. And in this case, bore pressure was not enough to create hydraulic fracture on the opposite side of the borehole. In case of high viscosity fluid injection, we always observed process of increase of bore pressure because fluid was unable to penetrate hydraulic fracture fast enough. But in case of water injection, it was penetration of fluid inside open hydraulic fracture as soon as fracture propagates. And in this case, it creates completely different pattern. Also, I would like to point out your attention on time scale. The time duration of propagation marked by this color bar, it's only 1.5 seconds. That in case of water injection, we had a very fast propagation, only 1.5 second propagation of 5.5 inches distance. And we found that the speed of hydraulic fracture propagation, just obtained directly from a cloud of acoustic emission events, appears to be 1,000 times faster in case of water injection than in case of high viscosity fluid injection. We had exactly the same injection rate, 5 milliliters per minute in both cases. But in case of high viscosity fluid, we observed slow propagation of hydraulic fracture. And in case of water injection, it was a really fast propagation of hydraulic fracture. Also, we have completely independent information about obtained from volume of flat jacks. In case of high viscosity fluid injection, we observed significantly wider. In the previous slide, it was something around 8 milliliters of fluid pushed by flat jacks. In case of water injection, it was less than half milliliter of water pushed by flat jacks. It means that fracture is significantly more narrow in case of water injection. And then next slide shows just a comparison of two cases. I hope that I can activate both of them, and you can see a comparison. It was the same material, the same shale. Two blocks were obtained just one near to each other, but you can see a completely different pattern of hydraulic fracture. We injected fluid with the same injection rate. It was the same stress applied to the block. The only difference is viscosity. In case of high viscosity, it was 2.5 million, and water is significantly low viscosity. And we observed a completely different process and different dynamic of hydraulic fracture propagation. And in all our other tests performed with the shale, we always found that in case of high viscosity fluid, we observed slower propagation of hydraulic fracture with wider opening, and there is a tendency of cross some interfaces and bedding planes in case of high viscosity fluid. But with the high viscosity fluid, it was necessary to pump bore fluid up to very high bore pressure, and therefore it's completely different processes. And in case of water injection, the bore pressure at which we observed the breakdown was a few times lower, but the fracture was also more narrow and propagating significantly faster than in case of high viscosity fluid injection. And therefore, the series of our research demonstrated the strong influence of fluid viscosities and injection rate on all dynamic of hydraulic fracture propagation. And it's just necessary to take into account in case of planning any hydrofracture work in the field. And just as a conclusion, I can tell you that during our series of our research, we have found strong correlation between independently measured volumetric deformation and distribution of acoustic emission events. Also, acoustic emission and ultrasonic transmission and volumetric measurements indicate initiation of a fracture process with the high viscosity fluid much earlier than maximum bore pressure. It was confirmed by the independent measurement. Acoustic emission fracture mapping correlates well with the actual fracture geometry from test analysis and with the ATM analysis of fracture rock. And we have investigated the effect of interfaces on fracture propagation, as I described in my presentation. And acoustic emission analysis show us that fracture geometry in the shale with the strong fabric depend strongly on the fluid viscosity and rock fabric. And definitely it's necessary to take into account always during planning of acoustic emission or of hydraulic fracture job. And in the end, I would like to thank my colleagues, because we performed this series of research together with TerraTek and Innovation Center colleagues, and some of them are right now during this presentation, and I really thank whole group of our researchers. And now I'm ready to answer your questions. Thank you for your attention.
Any questions?
One of the slides where the waterfront moved from bottom to top.
Yeah. Yeah, I can put this slide very quickly. Yes. This one. Yeah.
And it means that the acoustic emission activity decreases as the waterfront moves to the top.
Yes.
What would be the possible reason?
The possible explanation is very easy, delta P. Because during the process of propagation, we especially made a calculation that when we applied 5 MPa bore pressure at the bottom, there is a sharp gradient of bore pressure distribution. But later, during propagation, the pressure profile became really smoother and smoother. And therefore, at the end, on the propagation of water through the second part of the sample, it was not enough additional pressure by waterfront in order to induce fracture. We have completely independent measurements of this trace, number 5, ultrasonic transmission, that definitely water propagated through this region. And also we have independent measurements of pore pressure at the top of the sample, that water reached the top of the sample. But this part of the sample was quiet. It was no induced acoustic emission activity induced by fluid injection. Because we have found in our research that in order to have induced acoustic emission activity, it's necessary to have two conditions. First of all, sample or local place of the sample should be very close to failure, and then it's necessary to have a pore pressure high enough to induce fracture in this particular place. And if we do not have these conditions on the upper part of the sample, it will be no induced acoustic emission activity, because it's really necessary to have this condition of sample being really very close to failure, and then it's possible to register induced acoustic emission. Yeah.
I don't know a lot about about fracking, but in a lot of instances they use propellant or props that keep the cracks open.
Yeah.
Did you use that in any of these experiments?
Yes, we used, and actually you can see on probably on this slide. Yeah. That we no, not on this one, but I think that in this test we used 100 mesh propans, and we found that in order to have a propan delivery, it's necessary to have a wide enough opening. We performed a series of tests with the propan, and in this particular test, we have found no presence of propans on the outside of the block. All propans were in the borehole, because the opening of the hydraulic fracture with the 1,500 centipoise fluid was not high enough to deliver propans. When we performed a similar test with the high viscosity fluid, as far as I remember, Jeff observed on the surface clearer propans with the same conditions, the same injection rate, the same thread conditions, but with the high viscosity fluid, we have propans delivery because we have evidence that propans were on the surface and also they were collected in some buckets after the test. And in this particular test, with the smaller viscosity fluid, it was no propans delivery at all. And therefore, for frac job in the field, always it's necessary to take into account that in order to deliver successfully propan to some certain place, it's necessary to have a wide, high enough opening of the fracture. And we found that only high viscosity fluid and high injection rate allow us to have high enough opening. And in this case, we have many examples of successful delivery of propans also in the shale. But in many cases, in case of shales with the presence of plenty of planes of weaknesses, it's very difficult to deliver propans because of some existence of planes of weaknesses, because we can induce some shearing along planes of weaknesses, and it will be not enough opening, and propans will be not delivered. And therefore, it's really very important to know what opening of hydraulic fracture we can estimate. And we found that the only way to deliver propan successfully to have high injection rate and high viscosity. Yeah.
So after you've initiated fracture and you stop pumping, you still have emissions.
Yeah.
Due to the rock reorganizing itself, and what can you infer from that?
Yeah. Just like in this example, or maybe this will be even better to show, and I can try to stop animation and the moment of beginning of fluid withdrawing. Yeah. For example, now I stopped at the moment of fluid withdrawing. Definitely, we are pumping back, but all the dynamic of hydraulic fracture propagation indicates that fracture is really very close to the surface, and we have a lot of stored energy in this fluid inside borehole. And fracture, if I continue animation, you see, we still have a process of fracture propagation even after withdrawing. And therefore, based on this experiment, we have learned that in order to arrest fracture, it's necessary to withdraw fluid really very fast. And in other tests that I demonstrated, I call it test number 3, when we really arrested fracture inside block, we withdrawn fluid with significantly faster withdrawing rate, because that's the only way to prevent fracture propagation toward the boundary, as the remove energy fast enough. And we demonstrated that we can do it successfully. Of course, in order to do it, it's necessary to identify reliably that we have a fracture, and then to take action and remove fluid very, very quickly. And we performed few tests pretty successful, and we know that as we demonstrated directly on the sink sections, that fracture was arrested. I especially made sink sections on the distances higher than B. It was no indication of fracture at all. It was just intact sandstone block without any presence of fracture. And therefore, we know how to arrest fracture, and acoustic emission allows to help to identify it at the moment of initiation.
How did you decide what to do at the bottom of the well bore, where you did your perforation? How did you decide what geometry to do, and how does that compare to, say, what's done in the field with casing and perforation?
Yeah, we performed, actually, as I mentioned, I'm in TerraTek 3 years, and during these 3 years, I know that we perform different kind of perforations. We had just like one of the simplest is sandblasting. We perform sandblasting on certain distance, and we can create sharp channels. We also had a helical perforation, and also we had an abrasive jetting tool that perform slots. And we have found that definitely this shape of perforation really has a lot of influence on initiation of hydraulic fracture. And we performed also many tests with just a small scratch on the surface in order to have very small stress concentration. And always we observe that with a very small stress concentration on the surface, we have a higher breakdown pressure, higher pressure of initiation. But if we would like to have initiation of hydraulic fracture at smaller pressure, then it's necessary to produce some stress concentration. And definitely it's a problem to scale to the field, because the diameter of our borehole in a small block test is only 1 inch. In the field, of course, it's much bigger. But we performed recently a series of tests on the large block where we used exactly the same size of the borehole, 3.5 inches in the field. And we tried to investigate the dependence of different kind of perforations. You're absolutely right that it's really very important, and that's in our to-do list to investigate in more details. And in order to scale to the field, it's a really serious problem. And we, in our group, in TerraTek, we have modeler, Jeff Burgard, and he works with modeling, try to estimate injection conditions similar to the field. And we found that it's possible to characterize injection with the with dimensionless viscosity. Injection rate and viscosity of fluid will be involved in these characteristics. And we try to model to make our laboratory test with the same value of this dimensionless viscosity as in the field. Of course, in the field they have pumping rate barrels per minute. We just unable to do it in laboratory. And also the size of the sample is maximum only 1 meter size. In the field, of course, it's much longer. But still we are trying to do this modeling and to investigate, first to investigate the processes in the small distance from the borehole. We just use exactly the same diameter as in the field. But in order to make a scaling, we use this comparison with different dimensionless viscosities.
The data